I would like to thank the organizer for letting me give a talk here. And today I will bring a presentation about the collider constraint on dark matter interpretation of the XENON1T access. This work is done in collaboration with Renat Primulandu and Patipan Utayara. Okay, this is the outline. First, I will give about the motivation. Second, I will talk about the boosted dark matter. Third, we will talk about the collider constraints and other physical constraints, and at the end, I will conclude. Okay, the motivation is based on the recent report XENON1T data that shows excess of electronic events with KEV recoil energy. Okay, although this can be in fact due to an unaccounted tritium background, something that we still don't know, it could be anyhow a hint of a new physics, and this in fact very interesting. And people in fact have worked on this new physics, and to name a few, it's not exhaustive list, just a few of them. We have the solar axion, large neutrino magnetic moment, bosonic dark matter, and boosted dark matter. And unfortunately, for the first two, solar action and large neutrino magnetic moment, although they can give a very good fit to the xenon access, but they are strongly constrained by stellar cooling. And for bosonic dark matter, it's not enough to get a good fit. And for boosted dark matter, it can give a good fit, and that's why it's very interesting if there is another the constraints that can further constrain this scenario. So the boosted dark matter come from the fact that the usual cold dark matter with a speed of 10 to negative 3 cannot cause such excess because its energy is too small. So its energy has to be boosted, and it must have speed around 0.1 for mass around MeV to 10 GeV. So this, in fact, the collaboration of Kashiwa et al. Has already worked on the fit that can give to the xenon access, and they found that the product of the number density of the dark matter times the free electron cross section has to be around 10 to negative 44 in per centimeter. So this in fact brings us two scenarios that can, in fact not two scenarios, several scenarios, but two scenarios that can be interesting to look at is the semi-annihilation process, where you have psi goes to annihilate to psi plus some other particle, and two component dark matter in which you have chi plus psi. And this is the second one is in fact that we will work on today. So we will consider the two component dark matter, chi and psi, and in which the fast moving dark matter or the boosted dark matter is called psi, and we have another set of dark matter chi, which is a little bit heavy, in order to suit the decay. So it is psi that will interact with the electron. So it will give the electron recoil through the following interaction. So from this interaction, we can directly calculate the free electron cross section, and we will require that the product of this quantity and the dark matter density will be 10 to the negative 44 in per centimeter. So from here, since the number density of the dark matter will correspond to the other astrophysical bounds, we can constrain the scenario through this relation. So we will, for the collider constraint, we will use the following experimental bounds. We will use the EU141 and NA64 that constrain Z prime into E plus E minus. We also work on the NA64 result that constrain Z prime to invisible. We will also use Babar collaboration for both the E plus E minus and invisible decays. We also use the Z to 4 lepton constraint. We also use the left search for neutralino without parity, the scheme, the neutralino without parity. And we also use the left search for monophoton. So bring all of them together, we get the following plot. This is the plot that we constrain only from the collider. So we will split the discussion in, because we have two coupling, a non-coupling, G psi and GE. So we split into this case of G psi equals to 1 and G psi equals to GE. And for G psi equals to 1, we could expect that the vast majority of the region is constrained by the Z prime decay to physical. So the same thing for the heavier scenario of the dark matter 10 GeV, we got the similar result, and also as expected, since now the dark matter is heavy, so the vast majority of the region is dominated by the Z prime to equals to minus. So using the result we got here, we can constrain the product of the dark matter number of density, and from there we can deduce the for instance the annihilation cross section. The annihilation cross section is obtained from the dark matter number of density, and we got the following plot. And in fact, this it has an upper bound coming from KKT bound. And we can see that because of the KKT bound, the mediator mass, the Z prime mass, is constrained quite strongly. It's about 300. It has to be less than 300 GeV for the M psi equals 1 to MeV, and it has to be less than about 50 MeV for M psi equals to 10 GeV. In fact, we could also, in principle, have the constant from CMB in which chi can be 10 to 40, but that depends strongly on the production mechanism that we will not address today. And also same thing for the decay width, since chi can also decays into the fast moving dark matter psi bar, and we are bounded to the edge of the universe bar. So unlike the annihilation case, for this case, the Z prime mass is also is not very strong. Also, for the last thing, the dark matter can also in principle be captured in the sun. And if we assume the equilibrium between the capture rate and the depletion rate, the number of density in fact is proportional to the dark matter and proton collision. We can get constraint from CMB and anisotropy, so we get the following bounds. Unlike the previous bound, this bound, especially for light dark matter, is not very strong. It's not very constrained. And yeah, for the case when G psi equals to GE, it is not very, it is constrained but not very much. So in the end, we conclude that we study color constraint from class of model that can explain the XENON1 quantum excess. We're having a fast moving dark matter scattered off an electron. So from there, we derive bounds on Z prime electron couplings and interpret them in terms of production mechanism. This bound should be applicable to any model where boosted dark matter interacts with an electron through. So thank you for your attention.